Hello, guys. Welcome to the last chapter of the future of humanity. Today, we're gonna be talking about living the universe. The Earth is dying. In the movie Interstellar, a strange blight has hit the planet, causing crops to fail and agriculture to collapse. People are starving. Civilization is slowly crumbling as it faces a devastating famine. Matthew McConaughey plays a former NASA astronaut who is given a dangerous mission. Earlier, a wormhole mysteriously opened up near Saturn. It is a gateway that will transport anyone who enters it to a distant part of the galaxy, where there might be a new inhabitable world. Desperate to save humanity, he volunteers to enter the wormhole and search for a new home for humanity amongst the stars. Meanwhile, back on Earth, scientists are desperately trying to find the secret of the wormhole. Who made it and why did it appear just as humanity was about to perish? Slowly, the truth dawns on the scientists. The technology to make this wormhole is millions of years more advanced than ours. The beings who made it are actually our descendants. The creators are so advanced that they live in hyperspace, beyond our familiar universe. They have built a gateway to the past to send advanced technology to save their ancestors. By saving humanity, they will actually save themselves. According to Kip Thorne, who in addition to being a physicist was one of the producers of the film, the inspiration for the physics behind the movie comes from string theory. If we survive, one day we will face a familiar crisis like this, except that this time the universe will be dying. One day in the far future, the universe will go cold and dark, stars will cease to shine as the universe is plunged into a big freeze. All life will stop moving. But the question is, are there any loopholes to escape this? Can we avoid this cosmic doom? Can we, like Matthew, find salvation in hyperspace? In order to understand how the universe might die, it is important to analyze the predictions of the far future given to us by Einstein's theory of gravity, and then analyze the startling new revelations that have made it in the last decade. According to these equations, there are three possibilities for the ultimate fate of the universe. The first is the Big Crunch, when the expansion of the universe slows down, stops and reverses itself. In this scenario, the galaxies in the heavens will eventually halt and begin to contract. Temperatures will rise dramatically as the distant stars come closer and closer. Eventually, all the stars coalesce into a primordial superheated mass. In some scenarios, there might even be a big bounce and the Big Bang could start all over again. The second is the Big Freeze, when the growth of the universe continues unabated. The second law of thermodynamics states that total entropy always increases, so eventually the universe will go cold as matter and heat become more diffuse. The stars will cease to shine and the night sky will become totally black, and temperatures will plunge to near absolute zero, when even molecules cease almost all of their motion. For decades, astronomers have been trying to determine which scenario determines the fate of our universe. This is done by calculating its average density. If the universe is dense enough, then there is enough matter and gravity to attract the distant galaxies and reverse the expansion, so that the Big Crunch becomes a realistic possibility. If the universe lacks sufficient mass, then there is not enough gravity to reverse the expansion and the universe goes into a big freeze. The critical density separating these two scenarios is roughly 6 hydrogen atoms per cubic meter. Both in 2011, the Nobel Prize in Physics was given to Saul Perlmutter, Adam Rees and Brian Schmidt for a discovery that overturned decades of cherished belief. They found that the universe, instead of slowing down in its expansion, was actually speeding up. The universe is 13.8 billion years old, but about 5 billion years ago it began to accelerate exponentially. Today the universe is expanding in a runaway fashion, Scientific American claimed. The astrophysical community was stunned to learn that the universe was driving itself apart. These astronomers came to this astounding conclusion by analyzing supernova explosions in distant galaxies to determine the rate at which the universe expanded billions of years ago. When analyzing this supernova, scientists found that they were moving away from us, just as expected, but to their shock, they found that closer supernovae appeared to be moving away more rapidly than they should, indicating that the rate of expansion was accelerating. So in addition to the Big Freeze and Big Crunch, a third alternative began to emerge from the data, the Big Rip, which is like the big freeze on steroids. It is a vastly accelerated timeframe for the life cycle of the universe. In the Big Rip, the distant galaxies eventually move away from us so fast that they exceed the speed of light and disappear from view. This means that the night sky will become black, because light from the distant galaxies is moving away so quickly that it cannot reach us. Eventually, this exponential expansion becomes so great that not only is the galaxy torn apart, the solar system is ripped apart, and the very atoms making up our bodies are also torn apart. Matter as we know it cannot exist in the final stages of the Big Rip. Scientific American writes, galaxies will be destroyed, the solar system will combine, and eventually all the planets will burst asunder as the rapid expansion of space rips apart its very atoms. Finally, our universe will end in an explosion, a singularity of literally infinite energy. Bertrand Russell, the great British philosopher and mathematician, once wrote, all the devotion and all the inspiration, all the noonday brightness of human genius are destined to extinction in the vast death of the solar system, and the whole temple of man's achievements must inevitably be buried beneath the debris of a universe in ruins. Only within the scaffolding of these truths, only on the firm foundation of unyielding despair, can the soul's habitation henceforth be safely built. Russell wrote about a universe in ruins and unyielding despair in response to predictions by physicists of the Earth's eventual demise, but he did not foresee the coming of the space program. He did not foresee that advances in technology might allow us to escape the death of our planet. But although we might one day be able to avoid the death of our sun with our spaceships, how will we avoid the death of the universe itself? The ancients, in some sense, anticipated many of these violent scenarios. Every religion, it seems, has some mythology to explain the birth and death of the universe. In Norse mythology, the twilight of the gods is called Ragnarok, the day of reckoning, when the world is blanketed in unending snow and ice and the heavens freeze over. The world witnesses the final battle between the frost giants and the Norse gods of Asgard. In Christian mythology, we have Armageddon, when the forces of good and evil clash for the last time. The four horsemen of the apocalypse appear, foretelling the final judgment. In Hindu mythology, there is no final end of days at all. Instead, there is an unending series of cycles, each lasting about 8 billion years. But after thousands of years of speculation and wonder, science is beginning to understand how our world will evolve and eventually die. For the Earth, the future lies in fire. In 5 or so billion years, we will have the last nice day on our home planet, and then the sun will exhaust its hydrogen fuel and expand into a red giant star. Eventually, the sun will set the sky on fire, the oceans will boil, and the mountains will melt. The Earth will be engulfed by the sun and will orbit like a burnt-out cinder within its fiery atmosphere. There is a biblical reference that says, "From ashes to ashes, dust to dust." Physicists say from stardust we came, to stardust we will return. The sun itself will suffer a different fate. After the red giant phase, it will eventually exhaust all its nuclear fuel, shrink and go cold. It will become a small white dwarf star about the size of the Earth and eventually die as a dark dwarf star, a piece of nuclear waste drifting in the galaxy. Unlike our sun, the Milky Way galaxy will die in fire. About 4 billion years from now on, it will collide with Andromeda, the nearest spiral galaxy. Andromeda is roughly twice the size of the Milky Way, so it will be a hostile takeover. Computer simulations of the collision show that the two galaxies will enter a death dance as they orbit around each other. Andromeda will rip off many of the arms of the Milky Way, dismembering it. The black holes and the center of both galaxies will orbit around each other and finally collide, merging into a bigger black hole, and a new galaxy will emerge from the collision, a giant elliptical galaxy. In each of these scenarios, it is important to realize that rebirth is also part of the cosmic cycle. Planets, stars, and galaxies get recycled. Our sun, for example, is probably a third-generation star. Each time a star explodes, the dust and gas it spews into space receive the next generation of stars. Science also gives us an understanding of the life of the entire universe. Until recently, astronomers thought that they understood its history, an ultimate fate of trillions of years into the future. They had speculated that it is evolving slowly in 5 epochs. In the first epoch, the first billion years after the Big Bang, the universe was filled with hot, opaque clouds of ionic molecules, too hot for electrons and protons to condense into atoms. In the second epoch, a billion years after the Big Bang, the universe cooled down so that atoms, stars, and galaxies could emerge from the chaos. Empty space suddenly became crystal clear, and stars lit up the universe for the first time. We are living in this era now. In the third epoch, about 100 billion years after the Big Bang, the stars will have exhausted most of their nuclear fuel. The universe will consist mainly of small red dwarf stars, which burn so slowly that they can shine for trillions of years. In the fourth epoch, trillions of years after the Big Bang, all the stars will finally burn out and the universe will go completely black. Only dead neutron stars and black holes remain. In the fifth epoch, even black holes begin to evaporate and disintegrate, so the universe becomes a sea of nuclear waste and drifting subatomic particles. With the discovery of the accelerating universe, this scenario might be compressed into billions of years. The Big Rip upsets the entire apple cart. What is causing this sudden change in our understanding of the ultimate fate of the universe? According to Einstein's theory of relativity, there are two sources of energy that drive the evolution of the universe. The first is the curvature of space-time, which creates the familiar gravity field surrounding the stars and galaxies. This curvature is what keeps our feet on the ground. This is the energy source most studied by astrophysicists. But there is also a second source of power which is usually ignored. It is the energy of nothingness, the energy of the vacuum called dark energy. The very emptiness of space contains energy. The most recent calculations show that this dark energy acts like an anti-gravity and it is pushing the universe apart. The more the universe expands, the more dark energy there is, which causes it to expand even faster. At present, the best data indicate that about 69% of the matter and energy in the universe is contained in dark energy. So dark energy, which is pushing the galaxies away from us, is clearly the dominant force in the universe, much larger than the energy contained in the curvature of space-time. One of the central problems in all of cosmology is therefore to understand the origin of this dark energy. Where does it come from? Will it ultimately destroy the universe? Usually when we simply combine relativity and the quantum theory in a crude shotgun marriage, we can get a prediction for dark energy, but the resulting prediction is off by a factor of 10 to the 120, which is the biggest mismatch in the history of science. Nowhere do we find a discrepancy this large. It indicates that something is terribly wrong with our understanding of the universe, so the unified field theory, instead of being a scientific curiosity, becomes essential to understanding how everything works. The solution to this question will tell us the fate of the universe and all the intelligent creatures in it. Given that the fate of the universe is likely to die a cold death in the distant future, what can we do about it? Can these cosmic forces be reversed? There are at least three options. The first is to do nothing and let the life cycle of the universe play out. As it gets colder and colder, intelligent beings will adjust and think slower and slower, according to physicist Freeman Dyson. Eventually, a simple thought may take millions of years, but these beings will never notice because all other beings will think slower as well. It will be possible to have intelligent conversations between these beings, even if it takes millions of years. So from this point of view, everything will seem normal. Living in such a cold war may actually be quite interesting. Quantum leaps, which are extremely unlikely in the human lifespan, may begin to occur routinely. Wormholes may open up and close before our eyes. Bubble universes may pop out in and out of existence. These beings may seem there like our brains operate there slowly. However, this is only a temporary solution, because eventually molecular motion will become so slow that information cannot be transferred from one place to another. At this point, all activity, including thinking, no matter how slow, will cease. One desperate hope is that the acceleration caused by dark energy will suddenly disappear all by itself before this happens. Since no one knows why the universe is accelerating, there is that possibility. In the same vein, the second option is that we evolve into a Type 4 civilization and learn to utilize energy beyond our own galaxy. I once gave a talk on cosmology and discussed the Kardashev scale. Afterward, a 10-year-old boy came up to me and I said I was wrong. There must be a Type 4 civilization beyond the usual Type 1, 2, and 3 of the Kardashev classification. I corrected him and told him that there were only planets, stars, and galaxies in the universe, and that hence a Type 4 civilization is impossible. There was no energy source beyond the galaxy. Later, I realized that perhaps I was too impatient with the boy. Remember that each type of civilization is 10 to 100 billion times more powerful than the previous type. Since there are about 100 billion galaxies in the visible universe, a Type 4 civilization could harness the energy of the entire visible universe. Perhaps the extragalactic energy source is dark energy, which is by far the largest source of matter and energy in the universe. How might a Type 4 civilization manipulate that dark energy and reverse the Big Rip? Because by definition a Type 4 civilization can harness extragalactic energy, they might manipulate some of the extra dimensions revealed by string theory and create a sphere in which dark energy reverses polarity so that the cosmic expansion is reversed. Outside the sphere, the universe might still be expanding exponentially, but inside the sphere the galaxies evolve normally. In this way a Type 4 civilization could survive even if the universe is dying all around it. In some sense it would act like a Dyson sphere, but although the purpose of the Dyson sphere would be to trap sunlight inside, the purpose of this sphere would be to trap dark energy, so that the expansion could be contained. The final possibility is to create a wormhole through space and time. If the universe is dying, then one option might be to leave it and enter a younger one. The original picture given to us by Einstein is that the universe is a huge expanding bubble. We live on the skin of the bubble. The new picture given to us by string theory indicates that there are other bubbles out there, each one a solution to the different string equations. In fact, there is a bubble bath of universes creating a multiverse. Many of these bubbles are microscopic and pop into existence in a mini Big Bang and then rapidly collapse. Most of them are of no consequence to us, since they live out their short lives in the vacuum of space. Stephen Hawking has called this constant churning of universes in the vacuum the space-time foam, so nothingness is not empty but is full of universes in constant motion. Strangely, this means that even within our bodies there are vibrations within the space-time foam, but they are so tiny that we are blissfully unaware of them. The startling aspect of this theory is that if the Big Bang happened once, it can happen again and again. So a new picture emerges of baby universes budding from other universes, and our universe is nothing but a tiny patch of a much larger universe. As we saw previously, an advanced civilization might be able to build a gigantic particle accelerator the size of the asteroid belt that could open up a wormhole. If it is stabilized by negative energy, then it might provide an escape route to another universe. We have already discussed using the Kashmir effect to create this negative energy, but another source of negative energy is these higher dimensions. They may serve two purposes. They may change the value of dark energy, thereby preventing the Big Rip, or they might create negative energy to help stabilize a wormhole. Each bubble or universe in the multiverse has different laws of physics. Ideally, we want to enter a parallel universe where atoms are stable, but the amount of dark energy is much lower, so that it expands enough to cool down and allow habitable planets to form, but not so much that it accelerates into an early big freeze. All these speculations at first seem preposterous, but the latest cosmological data from our satellites seems to support this picture. Even the skeptics are forced to admit that the multiverse idea is consistent with the theory called inflation, which is a supercharged version of the old Big Bang theory. In this scenario, just before the Big Bang, there was an explosion called inflation that created the universe in the first 10 to the minus 33 seconds, much faster than the original theory. This idea, originally proposed by Alan Guth of MIT and Andrei Linde of Stanford, solved a number of cosmological mysteries. For example, the universe seems much flatter and more uniform than predicted by Einstein's theory, but if the universe underwent a cosmic expansion, it would flatten out, much like inflating an enormous balloon. The surface of the inflated balloon seems flat because of its size. Also, when we look in one direction of the universe and then look 180 degrees in the opposite direction, we see that the universe is pretty much the same no matter where we look. This requires some form of mixing between its different parts. but because light has a finite velocity, there is simply not enough time for information to travel across these vast distances. Hence, the universe should look lumpy and disorganized because there was not enough time to mix the matter. Inflation solves this by postulating that at the beginning of time, the universe was a tiny patch of uniform matter. As inflation expanded this patch, it created what we see today, and because inflation is a quantum theory, there is a small but finite probability that it can happen again. Although the inflation theory has had undeniable success in explaining the data, there is still a debate amongst cosmologists as to the underlying theory behind it. There is considerable evidence from our satellites that shows that the universe underwent a rapid inflation, but precisely what drove this inflation is not known. So far, the leading way to explain inflation theory is through the string theory. I once asked Dr. Good if it might be possible to create a baby universe in the laboratory. He replied that he actually did the calculation. One would have been able to concentrate a fantastic amount of heat at one point. If the baby universe were to be formed inside the lab, it would explode violently in a big bang. However, it would explode in another dimension, so, from our point of view, the universe would vanish. However, we'll still feel the shock wave of it being born, which would be equivalent to the explosion of many nuclear weapons. So he concluded that if we did create one, we would have to run very quickly. The universe can also be viewed from the perspective of theology, where all religions follow into two categories: religions in which there was an instant of creation, and religions that are eternal. For example, the Judeo-Christian philosophy talks about a creation, a cosmic event when the universe was formed. However, in Buddhism there is no God at all. The universe is timeless, with no beginning or end. There is only nirvana. These two philosophies seem totally in opposition to each other. Either the universe had a beginning or it didn't. But a melding of these two diametrically opposed philosophies is possible if we adopt the multiverse concept. In string theory, our universe did in fact have a cataclysmic origin, the Big Bang, but we live in a multiverse of bubble universes. These bubble universes in turn are floating in a much larger area, a 10-dimensional hyperspace which has no beginning. So Genesis is happening all the time within the larger arena of Nirvana. This then gives us a simple and elegant unification of the Judeo-Christian origin story with Buddhism. Our universe did in fact have a fiery beginning, but we coexist in a timeless Nirvana of parallel universes. This takes us back to the work of Olaf Stapledon, who imagined that there is a star maker, a cosmic being that creates and discards entire universes. He is like a celestial painter, constantly conjuring up new universes, thinking with their properties and then moving on to the next one. Each universe has different laws of nature and different life forms. The star maker himself was outside these universes and could see all of them in their totality as he painted on a canvas of the multiverse. Stapledon writes, "Each cosmos was itself gifted with its own peculiar time, in such a manner that the whole sequence of events with any single cosmos could be viewed by the star maker, and not only from within the cosmical time itself, but also externally, from the time proper to his own life, with all the cosmical epochs coexisting with each other." This is very similar to the way in which string theories view the multiverse. Each multi-universe is a solution of the string theory, each with its own laws of physics and with its own timescales and measurements. As Stapledon said, one must be outside of normal time and outside of all of these universes to see these bubbles all at once. But if we have a bubble bath of possible universes, then which one is ours? This raises the question of whether the universe was designed by a higher being or not. When we examine the forces of the universe, we find that it seems to be tuned just right to make intelligent life possible. For example, if the nuclear force were a bit stronger, the sun would have burned out millions of years ago. If it were a bit weaker, the sun would never have ignited in the first place. The same applies to gravity. If it were a bit stronger, we would have had a big crunch billions of years ago. If it were a bit weaker, we would have had a big freeze instead. In both cases, the nuclear and gravitational forces are tuned just right to make intelligent life on Earth possible. When we examine other forces and parameters, we find the same pattern. Several philosophies have emerged to address the problem of the narrow range of these fundamental laws that could allow life. The first is the Copernican principle, which simply states that there is nothing special about the Earth, so the Earth is just a piece of cosmic dust wandering aimlessly through the cosmos. It is just a coincidence that the forces of nature are tuned just right. The second is the anthropic principle, which states that our very existence places enormous constraints on what kind of universes can exist. A weak form of this principle simply says that the laws of nature should be such that life is possible, since we exist and are contemplating those laws. Any universe is just as good as any other, but only our universe has intelligent beings who can ponder and write about this. But a much stronger version states that it is so unlikely that intelligent life exists that perhaps the universe is compelled in some way to allow intelligent life to exist, that perhaps the universe was designed for it to be so. The Copernican principle says that our universe is not special, while the anthropic principle says that it is. Strangely, while both principles are diametrically opposite of each other, they are both compatible with the universe as we know it. The way to resolve this problem without invoking religion is the existence of exoplanets, most of which are too close or too far from the sun to support life. We are here today because of luck. It was luck that we live in the Goldilocks zone around the sun. Likewise, the explanation for why the universe seems to be fine-tuned to allow for life as we know it is because of luck, because there are billions of parallel universes that are not fine-tuned for life, that are completely lifeless. We are the lucky ones who can live to tell about it, so the universe is not necessarily designed by a superior being. We are here to discuss the question because we live in a universe compatible with life. But there is another way to look at this problem. This is the philosophy that I prefer and the one that I am working on at present. In this approach, there are many universes in the multiverse, but most are not stable and will eventually decay down to a more stable universe. Many other universes might have existed in the past, but they didn't last and were subdued into ours. In this picture, our universe survives because it is one of the most stable. So my point of view combines both the Copernican and the anthropic principle. I believe that our universe is not special as in the Copernican principle, except for two features: that it is very stable and that it is compatible with life as we know it. So instead of having an infinite number of parallel universes floating in the nirvana of hyperspace, most of them are unstable, and perhaps only a handful of them survive to create life like ours. The final word on string theory has yet to be written. Once the full theory is solved, we can compare it with the amount of dark matter in the universe and the characteristics describing subatomic particles, which may settle the question of whether the theory is correct or not. If it is correct, string theory may also explain the mystery of dark energy, which scientists believe is the engine that may one day destroy the universe. And if we are fortunate enough to evolve into type 4 civilization capable of harnessing extragalactic power, then string theory may explain how the death of the universe itself may be avoided. Perhaps some enterprising young mind reading this book will be inspired to complete the last chapter in the history of string theory and answer the question of whether the death of the universe can be reversed. Isaac Asimov once said that all of the short stories he has written, his favorite was The Last Question, which gave a startling new vision of life trillions of years into the future and explained how humanity might confront the end of the universe. In that story, people have asked over the aeons whether the universe must necessarily die or whether it was possible to reverse the expansion and prevent the universe from freezing over. When asked, can entropy ever be reversed, the master computer replies each time, there is insufficient data for a meaningful answer. Finally, in the far future, trillions of years from now, humanity has outgrown the confines of matter itself. Humans have evolved into pure energy beings that can transport themselves across the galaxy. Without the shackles of matter, they can visit the far reaches of the galaxy as pure consciousness. Their physical bodies are immortal but stored in some distant, forgotten solar system so that their minds are free to roam. But each time they ask the fateful question, can entropy be reversed, they get the same response: there is not enough data. Finally, the master computer is so powerful that it cannot be placed on any planet and is housed in hyperspace. The trillions of minds that make up humanity fuse with it. As with the universe enters its final death throes, the computer finally solves the problem of reversing entropy. Just as the universe dies, the master computer declares, Let there be light, and there was light. So ultimately the future of humanity is to evolve into a god that can create an entirely new universe and begin again. This was a masterful work of fiction, but let us now analyze this short story from the point of modern physics. As we mentioned in the last chapter, we might be able to laser port our consciousness at the speed of light within the next century or so. Eventually, laser porting may become a vast intergalactic superhighway, carrying billions of minds racing across the galaxy. So Asimov's vision of beings of pure energy exploring the galaxy is not such a far-fetched idea. Next, the master computer becomes so large and powerful that it has to be placed in hyperspace, and eventually humanity merges with it. Maybe someday we can become like the Star Maker, and from our vantage point in hyperspace, look down and see our universe, coexisting with other universes in the multiverse, each containing billions of galaxies. Analyzing the landscape of possible universes, we may choose a new universe that is still young, that can provide a new home. We will choose a universe that has a stable matter like atoms and is young enough that stars can create new solar systems to spawn new forms of life. So the distant future, instead of being a dead end for intelligent life, might see the birth of a new home for it. If this is the case, then the death of the universe is not the end of the story.